So in this video I'm going to explore the sets created by taking an element of a group G and raising that element to integer powers. We'll show that these sets are groups, and then we'll explore the order of the sets and the order of the elements in the sets, and we'll show that these are equal. So the order of A, the set, is the number of elements in A. The order of little a, the element of the set, is the smallest integer for which the element raised to the power of the integer is equal to the identity e. So, for example, let's take two integers p and q. If we have a to the p equals a to the power of q equals e, then the order of A will be the smaller of P and Q. And let me just write out the set. So it's the integer powers of A. So we'll just show the ones around 0. So this is our set A. Now to show this as a group, we'll use the group axiom. So first of all, associativity. Well, this is straightforward because associativity is just inherited from the group G. Closure. Let's take two elements of A, so we'll have A to the power of m1, A to the power of m2. And we'll multiply these, so a to the power of m1 multiplied by a to the power of m2 equals a to the power of m1 plus m2. Now m1 and m2 are both integers, so certainly m1 plus m2 is an integer, so we can say that a raised to the power of m1 plus m2, little a raised to the power of m1 plus m2 is in the set big A. Now 0 is an integer, so little a to the power of 0 is e, the identity, so the identity is in the set. And finally, for an element a to the power of m, we can write the inverse of a to the power of m as a to the negative m. Let's just see why. So a to the power of m multiplied by a to the power of negative m equals a to the power of m minus m equals a to the power 0 equals e. So we can see the four group axioms are all obeyed, which means that our set A is a group. Now, for the next stage, I want to explore the order of the group A, which is the number of elements in A, and the order of little a, where little a is the generating element, and we'll see how these are related. So supposing we have two integers m and l, and suppose that a to the power of m equals a to the power of l, implies that m and l are equal, are identical. Well, if this is true, it means that the order of the group A is infinite, because no integer powers of A will be equal unless they share the same integer. So unless m equals l, the integer powers cannot be equal. So there will be an infinite number of them, and in this case we say that the order of A is infinite. and that we find that define the order of little a as being infinite too. And this makes sense because unless apart from a raised to the power of 0, there will be no other integer for which a to the power of the integer is the identity. So what we need to consider now is the situation where the orders of big A and little a are not infinite. So let's supposing we have a situation where there are two integers m and l, and they're non-equal integers, and we'll arbitrarily say that m is greater than l. And for these two integers, it's true that a raised to the power of m is equal to a raised to the power of l. Now let's explore where this leads us. So if we take a raised to the power of m minus l, we can see that this is equal to a raised to the power of m multiplied by a raised to the power of minus l. But a raised to the power of m is equal to a raised to the power of l, so we can write this as a to the power of l multiplied by a to the power of negative l equals a to the power of l minus l equals a to the 0 equals e. So a to the power of m minus l equals e, which means that n, which is the order of little a, must be less than or equal to m minus l, because remember the order of a is the smallest possible integer, for which a to the power of the integer is the identity. Now what I claim next is that for any integer power of a between 0 and a to the power of a to the power of n minus 1, I claim that all these integer powers of a are distinct. In other words, none of them is equal. So let's just show this by a very brief contradiction argument. So let's suppose that order of a equals n, and let's suppose for the sake of contradiction that two of these elements, these powers of a, are equal. So we'll call the two powers m and l. So we'll say that a to the m equals a to the l, with l's greater than or equal to 0, m is greater than l, and m is less than n. So l and m are integers between 0 and n minus 1. Well, if a to the m equals a to the l, then a to the m minus l equals the identity from up here, which means that m minus l, which is not equal to n, which is less than n, is the order of a. So which means that n is not equal to the order of a, which is a contradiction because we started off by saying that n was equal to the order of a, and in this case m minus l equals the order of a. So we've shown that all the elements of a, all the powers of a from 0 to n minus 1 are distinct. So I'm going to draw our group, and I'm going to claim that the group A is exactly these elements. So all the powers of A from 0 to a to the power of n minus 1. I'll just write it down. Claim this is so for this to be the case, it has to be true that for an integer m, which is either greater than n minus 1 or less than 0, it must be true that a to the m equals a to some r, where r is greater than or equal to 0, is less than n, which is to say less than or equal to n minus 1. So we're saying that any integer power of a for a number m, for an integer m outside this range 0 to n minus 1 must be equal to an integer power of an integer between 0 and n minus 1. And if that is the case, then we can be sure that this is the whole group, and we will know the order of the group. So let's just prove this by reference to the division theorem. The division theorem states that for an integer m will be equal to n, which is in this case the order of little a. So m is equal to n times an integer q plus an integer r, where r is greater than or equal to 0 but less than n, which is to say less than or equal to n minus 1. So let's raise a to that power. So a to the power of m equals a to the power of nq plus r equals a to the power of nq times multiplied by a to the power of r equals a to the n, all raised to the power of q multiplied by a to the r. Now a to the n is the order of little a, and so a to the n is the identity, and the identity raised to the power of q is still the identity. So what we have shown that indeed a to the m does equal a to the r for r in the required range greater than or equal to 0, less than or equal to n minus 1. So just to make some space, so what we have shown is that the set A defined in our title here is indeed a group, and we've shown that the order of A equals n, where n is the order of the element little a, which is what was required. We can take this one step further and say that sometimes the group A will be equal to the whole group G, and if this is the case, we say that G is a cyclic group generated by little a, and we can write this as follows: G equals triangular brackets little a, the cyclic group generated by A.